Hey, my name is Jake. I'm a math tutor from Chicago, and in this video, I'm going to do a couple of ring theory exercises. So this is for one of my students who is preparing for an abstract algebra exam. If you're preparing for an exam and you're looking for a tutor to help you out, you can contact me at herndonmathservices.com. And on to the exercises. So this video is going to have two exercises. I'll just give exercise 1 and then do the solution, and then I'll give exercise 2 and I'll do the solution. So exercise 1 says, let R be a commutative ring with prime characteristic P, and let phi from R to R be the function defined by phi of x equals x to the pth power. Show that phi is a ring homomorphism. So before giving the solution, let me just remind you that the characteristic of a ring is the smallest non-negative multiple of the multiplicative identity that gives you the additive identity. So it's the smallest multiple of 1 that gives you 0. All right, and the solution goes like this. To check that phi is a ring homomorphism, we need to check 3 things. It preserves addition, it preserves multiplication, and it sends the multiplicative identity to itself. So I'm just going to check those things in order. So for all x and y in R, we've got phi of x plus y is equal to x plus y to the pth power. That's the definition of phi. And the binomial theorem says x plus y to the pth power is equal to this quantity, the sum from k equals 0 to p of p choose k times x to the p minus k times y to the k. So consider the binomial coefficients in the special case where k is between 0 and p, strictly between 0 and p. So in that case, the numerator is divisible by p, but the denominator is not divisible by p. And so that means that p choose k is an integer multiple of p. So just to demystify that as best I can, if I've got a fraction, but I know the fraction is an integer, then I can rewrite this equation as this. And then if I've got some prime that divides the numerator of the fraction, but not the denominator of the fraction, then I can conclude that n, the integer a over b, n, is divisible by p, because p divides a, so it divides b times n, but it doesn't divide b, so it has to divide n. So I always need to think through that whenever I'm going through this proof. All right, so it really depends on already knowing that p choose k is an integer. This weird looking fraction is not just a fraction, it's an integer. All right, moving on. As r has characteristic p, it follows that when you take this sum from k equals 0 to p, I'm going to bring out the 0th term up front, and I'm going to bring out the pth term in back, and just leave all the terms in the middle here. All of these middle terms are 0 because we're in a ring of characteristic p, and p choose k is a multiple of p. So you're just left with the first and the last terms. That's x to the p plus y to the p, and that's phi of x plus phi of y. So what was the point of that? Phi of x plus y is equal to this, which is equal to this, which is equal to this. And so phi of x plus y is equal to phi of x plus phi of y. And that says phi preserves addition. So that was the first thing we needed to check. And I should mention that this fact, x plus y to the p equals x to the p plus y to the p, that fact is often called the freshman's dream. So if you want to look it up, that's how you look it up. All right, for all x, y, and r, phi of x times y is equal to xy to the p, which is equal to x to the p times y to the p. This equality uses commutativity in the ring to get all the x's on the left and all the y's on the right. And this is equal to phi of x times phi of y. So that says that phi preserves multiplication. And any power of the multiplicative identity is the multiplicative identity. So phi of 1 is 1 to the p, which is equal to 1. So that's the last thing we had to check. Therefore, R is a ring homomorphism. And that's the end of the exercise. All right, exercise 2. It's to show that in the last exercise, it's important that P was a prime. If it was a composite number, it wouldn't work. So give an example of a commutative ring R with characteristic 4 such that phi from R to R, defined by phi of x equals x to the fourth, is not a ring homomorphism. So here's one example. Let R be z mod 4z adjoin x. So that's the ring of polynomials in the variable x with coefficients in z mod 4z. So we have this, and you might have to check this in your scratch work, but phi of x plus 1 is equal to x plus 1 to the fourth. If you expand x plus 1 to the fourth, you get x to the fourth plus 4x cubed plus 6x squared plus 4x plus 1. And now when you take the coefficients mod 4, this 4 goes away, this 6 becomes a 2, and this 4 goes away. So you get x to the fourth plus 2x squared plus 1. And then if we look at phi of x plus phi of 1, that's x to the fourth plus 1. So these two things are not equal because in this ring, 2x squared is not 0. So phi is not a ring homomorphism because phi of x plus 1 is not equal to phi of x plus phi of 1. So I think that should do it. So one last time, if you are looking for a math tutor, you can contact me at my website. It's herndonmathservices.com. All right then, bye.